So we've started to develop our material balances across various spaces, and we are interested in how the concentration might be varying in both time and space across some process unit. And what we're going to do now is consider some simple mass transfer cases. We want to develop the mass balances, and even though the situations might be quite different in each case, there is an underlying connection among them. There is a way to generalize all these situations, and in fact we'll show later on that with just one equation we can represent virtually any type of mass transfer situation. Before we get to that though, we will need to acquire some experience in developing such models and such descriptions, and what we are going to do is just develop these mass balances and these concentration profiles for case studies with a number of variations to them. And in all these developments, we are going to assume that our component B doesn't factor, so we are largely going to work on simplified versions of our material balances and then look at generalizing them later on. So in the class description and the class discussion that is in the previous video, we've already covered question 1 in some detail, so you can consider that the first type of problem. And then in question 2, we have a 2-compartment cell, and we have already developed the material balance for the concentrations in each cell. So we are going now to consider the variation on this problem where we do not have agitation. So let's skip ahead to that problem. So there's the question 1 problem description and solution with some Python code for us to view some profiles. And then in this question 2, this is the problem. So we've got some unit, and there's a membrane in the middle of that unit somewhere. And in that, that membrane is separating that unit into 2 compartments. So we have 2 compartments here, and this membrane is also permeable. That means your component can diffuse across that membrane and enter the other compartment. And in the first variant of this problem, we had perfect mixing in each compartment. So we had the mixers on full blast in here, and in fact you need infinite amounts of infinite energy to get perfect mixing, but we assume that anyway. And now we are interested in the variant of the problem with the agitators switched off. So we want to develop the material balances. And here's the solution when we do have perfect mixing. So you can refer to that class discussion that we just had, and we showed that in just sticking some arbitrary numbers in, we showed that due to diffusion across the membrane, the 2 concentrations in the 2 compartments eventually equilibrated to one steady value here. So that was no variant. And now if we switch off the agitator, right, and let's just go back here. If you switch off the agitators, and let's just talk about one compartment. Let's talk about this compartment here. So if you switch off the agitator, that means no more perfect mixing. Then that means that there is going to be a driving force in this direction. So because generally speaking there's a concentration difference between these 2 compartments, then there is a net flux either in this direction or in this direction. So with the net flux in this direction, we expect that there will be a concentration change across our space. So we are concerned with this problem, that if we look in just one compartment, so let's draw it like this. Let's say the membrane is sitting here, and that's the compartment there. We are concerned about concentration varying from the membrane looking further into the compartment. And we are worried about just one direction, right? So just along that direction. We aren't really worried about changes in this direction because there's no driving for there's no withdrawal of A in this direction, so there's no change in that direction. Similarly, there's no change in that direction. So if you look at this edge, nothing is happening on this face. There's no flux in this direction. So we're not worried about lateral or vertical flux. We're only worried about flux that's moving into the page, if you like. So flux in that direction. And so we are concerned that component A concentration might be changing in time and in the specific direction Z. And if you look at this face on the side, right? So imagine Z equals 0 here, Z equals L, the length here. So Z is changing in this direction, and then we can pick a specific point here, Z. So let's look at this face from this direction. So if you look at it in that direction, then you'll see the face like this. And then, as we say, we pick some position Z, and then let's just pick some small change from that delta Z. So we pick another point Z plus delta Z close by Z. And so we've got a thickness here of delta Z. And then if you imagine looking into the page here, there's some area inside the space, right? So if you look here, then there's some area here. So it will have an area like this. So that area just inside here at position Z, that's going to be the area going into the page here. So let's let that area be A. So A into the page times delta Z, the thickness, is going to be the volume of that part. And just note here, this is not the membrane. Just to clarify that, here's the membrane sitting out here, and we are not talking about the membrane now. We are just talking about some arbitrarily chosen space here, right? Because we want to write a mass balance across the space. We want to know how A is varying as we look away from the membrane, as we look into the compartment. So into the compartment, we need to just pick some arbitrary space, Z to Z plus delta Z, and write a balance there. And then hopefully that balance will tell us something about how A is varying across the space. So that's not the membrane, but it's just a chosen space, Z to Z plus delta Z. And we can say that our number of moles in the space is delta Na. And we say delta Na. Normally we write Na, we just write number of moles, but here we are choosing a specific sub-volume. So let's call this the sub-volume. So there's a thickness here, Z to Z plus delta Z, and then there's an area here. So we'll call that the volume, the sub-volume. So in that sub-volume, there's a certain number of moles, Na. So Na might refer to the whole compartment, the number of moles in the whole compartment. We don't want that. We want to talk about just that little sliver, that Z to Z plus delta Z sliver. So in that space, we'll call that delta Na. So delta Na is the number of moles in that space. Na is the number of moles in the whole space. So anyway, that's the number of moles in that little space, delta Na. And then the number of moles there is going to change depending on how much of A fluxes into this position Z. So you can see entering the space will be the flux at position Z. So there's a certain flux entering here. And then on this side, there's a certain flux leaving the space also. So any flux at Z plus delta Z means we are fluxing out of the space. Any flux at Z means we are fluxing into the space. So the flux at position Z times the area, that's the molar flow rate into our space. And then the flux at Z plus delta Z here times the area there, that's the molar flow rate out of the space. So the rate of change of moles in the space equals the flux times the area in here, and then the flux times the area out there. And then, of course, generally speaking, we have our molar flux written like this, and we interpret this as the diffusion gradient, the diffusion flux plus the convection flux. In this case, nothing's convecting. It's not as if there's some bulk flow rate of A. We've simply got a compartment, and we've stopped agitation, and there's no flow through that compartment. So there's no convection, so we can just ignore this part. And we can say the flux of A is just due to diffusion, like so. So we can substitute for Na in on the right-hand side here. And so you can see Na at Z is going to be dAB, dCA, dZ at Z. So we have to specify at Z because the gradient may be changing, right? If you go back here, you can see the gradient may be changing. The gradient might be sharp close to the membrane, and then looking further inside, the gradient might not be so sharp anymore. So the gradient is changing as Z is changing. So we specify at Z. Of course, dAB is a constant. Our diffusivity, we are assuming that's going to be constant, so we don't worry about this one too much. That's a constant in Z. And then, of course, that's just the flux. We have to multiply by the area to convert this to a molar flow rate, because the left-hand side is in terms of rate of change of moles. So we've got moles per second here. We need moles per second here. This is, of course, moles per second per square meter. So we need to multiply by area. So that's molar flow in. And then molar flow out is the diffusion flux, and this time it's at Z plus delta Z. So the gradient specifically at Z plus delta Z, and then you multiply by the area. So that's the right-hand side, and then of course the delta NA, the number of moles in the space, is equal to the concentration in the space. And of course here we should really say the average of the concentration between Z and Z plus delta Z, but we just call it CAZ here as an approximation, and we multiply by the volume. Later we'll see we take the limit delta Z going to 0, so that difference changes anyway. So anyway, the concentration in the space, that's what we mean there, multiplied by the volume, that's going to be the number of moles in the space. So the volume of the space, of course, is the area times the thickness there, delta Z. So in our balance, ddt of that delta NA becomes ddt of this thing. And of course, area and delta Z, those are constant with respect to t, so those can come out, and we've just got ddt of Ca. Now looking at this form, you can see A is appearing in each term, so we can just cancel all the A's, and then we can divide through by delta Z, of course, leaving us with ddt of Ca, and then 1 over Za times these things. Now look at this equation. You can see here, just imagine this as a function, right? You've got the same function here, and then you've got this function at Z plus delta Z minus the same function at Z, and then all divided by delta Z. So if you recall your derivative, this is in effect the same as the derivative of this function dab dc dz. That's of course if you let delta z go to 0. So if you apply limit delta z going to 0, then this is nothing but ddz of this thing. So ddz of this thing. And then if you look at this, of course, dab is a constant with respect to z, so we can just take that out as a constant, and then you've got ddz of Ca, so it's d2Ca dz squared. Right, so that's our balance, and I'm just going to write the slightly easier to see form. So we are saying that the concentration in the compartment is changing in response to gradients, second order gradients across the system, and we can see it's related to diffusivity, related to diffusion. Right, so that's our understanding of the system, and if you think about what this equation means, in fact, let's just sketch something here. So if you think about some values here, let's see, I need a brush instead. So let's say we have some space. Let's say these are different z values. Then let's imagine that we have a certain function above that. So let's say that's our concentration Ca there. So if you pick, let's say this is z, and this is, or let's number them. Let's say that z1, z2, z3. Now you can see that we've got a gradient across this concentration space, right? So there's a net gradient here. There's a certain positive gradient between C2 and C3 and C1.
Bixby voice privacy contents have been updated.
Ooh. Okay, so you can see here that let's focus on position 2. So you can see here that there are gradients in concentrations in the z direction. Now what we are interested in is with time, how is C2 changing? let's imagine time moving like this, right out of the page. So Z is along the page, and now we are interested in out of the page. So this, let's say this is at time t1, right? So let's say this whole line is drawn at t1. Then let's say there's another time here, t2. So we can imagine that if we look down here at z2, there's the point that corresponds to t2, and still looking at z1. Then we can imagine if we look up here, our c2 may have changed. So maybe c2 becomes this value next, right? So at t2, c2 might become this value. So this is c2 at t1. So it's we are numbering c according to the z position. So c in z2 is this value at t1, and then at time t2, c2 is some other value, so it's changed. So if you look further down time, c2 will be different. And you see that change is due to what the neighbors are doing. So if the neighbors c1 and c3 have a sharp gradient, then that might be causing c2 to shift about. Let's imagine it wasn't like this. Let's say C1, let's say the curve was actually like this. So if your neighbors here have higher concentrations, then C2 might be getting pulled upwards. So the tendency for C2 to change might be upwards. So currently it's here, but at the next time instant, C2 may have been pulled up here. And of course here I'm trying to talk in 3 dimensions, and it might be difficult to follow, so please backtrack on this video and be sure that you understand all the directions. But you see the concentration is changing as a result of the neighbors, as a result of changes in the neighbors. So I'm saying all this because when you look at a partial differential equation like this, these are the things that you want to go through your mind, right? You want to say that, look, the concentration in or the variable is changing in time due to changes in z. So due to changes of the concentration in the spatial dimension, there's going to be a change in the concentration. And if you think of this, we are typically talking about one value. So maybe let's just write it here explicitly. So let's say we are talking about the ith position. So Ca at Zi, so the concentration at some specific Z position. So A concentration is changing at that position Zi. So that's changing in time due to the gradients across that concentration. So due to what the neighbors are doing, right? That's how you can read this, right? The neighbors are causing there to be a net diffusion flux. That's going to cause A to change in time as well. And so you see in PDEs, they can look rather mysterious, right? If you don't think about what they mean, they can look like scary, arbitrary choices of derivatives. But actually, when you can see what they mean in terms of changes by the neighbors causing changes in time, then suddenly this thing has much more physical meaning. So always take time to appreciate what the equation is telling you. So differential equations, tremendously helpful. They just describe how changes are related to each other. So here the changes in time are related to the changes across space. That's what that equation is really telling us. So anyway, that's a description of how concentration changes in time and space across our compartment. And to solve an equation like this, we need boundary conditions, right? This is just an equation that describes how changes are related inside the space here. But if we want to know what it actually is, if we want to know what the concentration really is in the compartment, both in time and space, then we can't just describe changes, everything's changing, this change is related to that change. It's not enough. We also have to specify some additional information. So we need to nail down a solution, and the way we nail it down is by nailing down some edges here. We specify, oh yes, I know what's happening in time at this specific location, or at that location things are changing in this specific way. So if we add a bit more information and we constrain our solution in a particular way, then we can get a particular solution out of this quite general description. So this is very general. It's just telling us how changes are related to each other here. So there is a way to count up how much information you need to nail down a solution, and that is to look at each independent variable. So here we've got t and z as our two independent variables, and in t we have a first order derivative, in z we have a second order derivative. And by the way, just to clarify something, I'm just going to add here, let's say we had a k1 dca dz. So let's say we had this. So here, if we have k1 times dca dz, then it would still count as 2. So it's not as if having more derivatives add to the number of required boundary conditions. You still count this just as a 2. And also if you had another time derivative, so let's say we had k sub 2 dca dt, then this would still count as 1. So we need one boundary condition in t and two boundary conditions in z. So here's how we specify those boundary conditions. So here, if we consider at t equals 0 for all position z, we can say that, or we can claim that we know the concentration across the compartment. So the compartment, remember, started out perfectly mixed. So we had perfect mixing going on, and then at t equals 0, we removed the mixer. That means at least in the instant t equals 0, we still had the same concentration everywhere. So we can say at least at t equals 0, we have the same concentration Ca0. And so this is a boundary condition, which we usually call an initial condition. So in terms of time, those are special boundary conditions, a special case of a boundary condition, which we call initial conditions. So you can see here, initially everything was at that concentration Ca0. Now, that's of course 1, and we actually need 3 boundary conditions. So here's another boundary condition. So here we are saying that just to the right of this position z equals 0, right? So here's the compartment that we are modeling. Of course, there's another compartment on this side, and then this is the membrane in between. So this membrane has thickness lowercase delta, right? Now, just to the right of this membrane, we have a certain gradient here, and so this is looking into the compartment. So there's a gradient in there, dc dz, and let's call this position z, so the right edge of the membrane. So we know the membrane is very thin, but still we can talk about a left edge and a right edge. So let's call the right edge z equals 0. So to the right, which is z equals 0 plus, right, just past 0, right, z equals 0 plus, there's a certain flux, right? So there's a certain flux into the compartment, and then just to the left, which is z equals 0 minus, there's also a certain flux, and we know that's the flux through the membrane. Now, the space we are writing this over is this edge, right? It's not the membrane. The membrane is this whole thickness here. So we are just talking about the right face. Now, of course, a face is not a volume. A face is just, it has a 0 volume. There's no thickness to a face. It's just an interface. So there's it's not as if we can write rate of change of moles of A in the face, right? There's no thickness. The thickness, we can write rate of change of moles in the membrane, but that's not what we're saying. We are saying there's no rate of change in the face itself, the right face of the membrane. So the molar flux into the right face must equal the molar flux out of that right face. So that's what we're saying here. The flux in at z equals 0 minus, just to the left of that face, equals the flux out at the right face at z equals 0 plus. So those two fluxes are equal. So the flux on the left-hand side here, we know is going to be this. So if you go back to the previous section where we, in fact, it was the first problem in tutorial 3, we showed that for no convection, that we had a linear, that we could just take the difference in concentrations divided by the distance, and then that was basically our flux. So this is the flux through the membrane, and that's equal to the flux inside the compartment, just inside the compartment. So that's what we have. That's another boundary condition. And you see, this is different information. It's not the same as the information here, right? This is a relationship among the changes in time and space. This is about the initial condition. That's different information to that information. This also is different. The second boundary condition, which is about the flux across this face, that's new information. And of course you can cancel the diffusivities here. And then the third one is a bit less clear. So for the third one, we could say that at least initially, if we look far enough down the tube, then initially we haven't had any diffusion through the membrane as yet. So far enough down the tube, the gradient was still flat. So we could say that. But you see, that's not going to last very long. So we really need some other information. Maybe we can take another point in our fluid. We can say there's another point that's measurable, and so we could simply get another piece of information like that. But the point is, we need a third piece of information if we want to integrate this equation. We've got two pieces of information so far, but we need a third piece of information to have a hope of solving this. We'll come back to that. Right, for now, we want to ask, what about steady state? Can the system reach a steady state? And of course it can. So over time, this is going to reach some steady concentration profile, because in this situation you have a flux in and you have dispersion through the fluid. So we anticipate that there may be a steady state. It's not always automatic that you get a steady state, but let's say we do. So what would that look like? So at steady state, of course, our time gradients go to 0, so we can neglect that. So that's 0 equals this. And here everything is constant, so we can just integrate in z to give, so if you integrate this once, you get dc dz equals k. And of course here we've cancelled the dab with the 0 before doing the integration, so it looks like this. And then if you integrate this again, this is a constant in z, so if you integrate it, then that's k1z plus k2. Okay, so that's general, but we need these constants k1 and k2 before we can call this a solution. So to do that, let's use that first boundary condition. And by the way, we are not going to use the initial condition, right? So we had said, where is it? Here. We had said there's this initial condition that we could apply. But of course, now we are talking about steady state. So with steady state, we are talking about some point in the future where the whole system has steadied out. So the situation we are considering now doesn't have anything to do with time. So we can't use that initial condition. That information is not influencing this condition. Okay, so we use first the continuity of the molar flux condition. So if you take this equation, you can see dc dz is k1. So if we take dc dz at z equals 0, well, the z doesn't change anything here. So that's going to be dc dz. I'm not sure why I've got a k2 here. This should be k1. And then all this is what we just talked about. And so if you rewrite this, you can multiply the delta by the k1, and you can say CA at Z equals 0, so that's the same there, is equal to, and then that's K1 delta, and then plus CA2 at Z equals minus delta. And by the way, I've written it as minus delta because here, when we were writing this difference, this was, we defined this to be Z, and then the thickness is delta. So this is at position Z equals minus delta. So I forgot to explain this here. So anyway, we have this expression now, and so we've got K1 equals that. So we've rewritten this. So we've just taken this right hand side here and written this in terms of CA at Z equals 0. Now we could also apply that at Z equals 0, right? If you go back here, right, to our integrated form, if you apply Z equals 0, then the K1 will disappear, leaving us with just K2. So you can say CA at Z equals 0 equals K2. So CA at Z equals 0 equals K2. And then that's the same as CA at Z equals 0 equals all this stuff here. So you can bring that like so. And so looking at these two, you can say, well, back in my original equation here, in my integrated form, I can get rid of this K2. I've just found out that K2 is equal to this stuff here. So I can rewrite this as K1Z plus K2, where K2 is all that. Right? So we've now eliminated one of the unknown constants. We've eliminated that K2 by using our boundary condition. Now we need one other piece of information to solve this. So we could say, let's say our system reaches steady state, and we simply have available another measurement. So let's say we have at Z equals Z1. So Z1 is some position inside the compartment. Let's say we just stick a probe in and we measure the concentration there, and then we just use that information in here. So we apply CA at Z1. So here CA1. So at Z1, this is CA1. And then Z1, we can write that like that. And then this stays the same. And then that's there. So now we have another point, and so we can solve out for K1 here. So you can see here you've got K1 in these two, so you can say CA1 minus CA2 there, divided by, and you can group out K1 into Z1 plus delta, and then divide it. So if you have one more measurement, you can find K1 like this. And actually, you can show that the true steady state is a flat line here. Anyway, we'll see that in the next variation. Okay, so that's how you can solve the steady state version of this equation. But let's go back to the unsteady state version of this equation now. So in the unsteady state version, we have this balance, and we've got these conditions. This one we are a bit wary of, so let's not use this boundary condition. Let's not assume that it's a flat gradient at the end. So we've got two boundary conditions here. And we develop actually a numerical scheme for solving it here. So there will be an upcoming video on how to solve these problems numerically. You can read the stuff in the notes, so that's available now, but I don't want to distract from the physical reasoning at the moment, so I'm not going to go into this just yet. So I do show some results that were generated numerically, but we won't talk about how I did that. For now, let's just continue with deriving the equations and just look at the results and understand what they're saying. So we'll come back to this stuff. So here, if I apply those conditions, right, and here, actually, to solve it numerically, I did go ahead and use this this boundary condition. Where is it? I used this equation. I did use a flat gradient here, and you'll see in the results that what I've set up is that we have initially a value of 20, a concentration of 20 everywhere, and we have that at the interface, right, or rather across the interface, on the other side of the membrane, in the other compartment, the concentration was fixed at 10. So we were initially 20 in this compartment, and then we were exposed to 10 just on the interface. And here's what happens. So you can see here initially you were at 20, and then after some time you lost some of that concentration. So at the interface, right, so this is the Z position here. So Z equals 0, and then Z equals higher values. So we are looking down the tube this way. So this is right next to the membrane. So right next to the membrane, your concentration dropped initially, so that instead of 20 next to the membrane, the concentration went down, and you can see it kept going down until it reached the value across the membrane, which is 10. So as the concentration was dropping near the membrane, then component A was diffusing in to bridge that. From the bulk of the fluid, component A started diffusing towards the membrane. So it started getting depleted. So component A in this region, right, for these Z values, component A started diffusing in like so. So as the first bit diffused in, then that gave a lower concentration here. So then that called on more of the concentration to be to transfer towards the membrane. So component A was diffusing towards the membrane, so the concentration dropped quite sharply right next to the membrane, and so component A started diffusing in this direction until we got closer and closer to the equilibrium value of 10, and so eventually everything just settled out at 10. So this situation is a simplified version of this compartment problem. So in this case, I'm just fixing the concentration in the other compartment at a value of 10. I should really solve the same equation in the other compartment as well. So if you had started out at 10, it's likely that this would all steady out at 15 or something like that. So there's some intermediate concentration between the two compartments. So just for the sake of simplicity, I've applied a fixed value of 10 on the other side of the membrane. But if we solve them simultaneously, then you'll see that in the two, you would get, let's just sketch it here. So you would have that if this is Z equals 0, or Z equals 0, then you may have 20 here initially, and that would drop. So you would get, initially it was 20 and maybe 10 here, and then of course you've got the membrane in between. So you've got your membrane here. And so initially you had a very sharp gradient between the So initially you had a sharp gradient between the two, and then as more of A diffuses in here, so A starts to diffuse in, here, then of course you've got A coming in here, and so then A can diffuse in there, and then because now the concentration here is lower, more of A will be diffusing in, and so more of A will be penetrating here, and so eventually the two concentrations in the two cells are going to reach the same value. where there's no net driving force. So that's actually what happens. But what I've done in doing that numerical simulation is just fixed a number just to simplify that. But it's the same shape. Something you can also notice is that I fixed the end gradient to be 0, and you can see there's a flat line here that's shifting around. So that's there. Okay, so that's our no agitator variant of question 2.